Alright, so this video is going to be over squeeze theorem, also called sandwich theorem. It's a pretty nice, pretty easy theorem dealing with this triple inequality and the limit of that triple inequality. Let's read the theorem, get a little bit confused, then we'll do the first example, and hopefully that'll make a little bit more sense. Okay, so we have if h is less than or equal to f, which is less than or equal to g, for all x in the open interval containing c, except possibly at c itself, and if the limit of h is L, some number, and the limit of g is that same exact number, and they're both approaching that same value of c, then the limit for the middle function, as x is also approaching c, is going to be that same value L. So basically it says, if the limit for this bottom function is one number, and the limit for the top function, if those are the exact same numbers, like if this is L and this is L, well then the limit of the middle function, since it's bounded between the bottom and the top, the limit for that middle function must also be that same number. It's important that the limits match. Like if this was A and then that was A and then this was asking about B, sorry. Or if this was A and then this was B, sorry, it's not going to work, right? But you know, if you're looking at the same part of all three graphs, if the top and the bottom have the same limit and this inequality is true, then you know the middle function must also have the same limit. So let us go through and do this first example. Here we go. I'm going to graph them. 2 is a horizontal line. That's pretty easy to graph. So I'll do that one with blue. And then we'll graph the parabola that shifted up 2 units. So I know those are going to intersect. And here it doesn't tell me anything about the f function, right? I don't know what that graph really looks like. All I know for surezies is that f, whatever that function is, it's going to be above the line but below the parabola, right? It's always going to be between those two. I don't know anything else about it, but I do know those two facts. So it could be something really crazy like this. You just don't really know. But it's bounded between the horizontal line and then the parabola. So let us investigate some facts. Let's take the limit, right? We want to know the limit as x is approaching 0 of that middle unknown function f. Let's see what we can tell about the outside two functions. The limit as x is approaching 0 of 2, right? The bottom function. Well, that's 2. Let's take the limit as x is approaching 0 of the top function. This one you could direct evaluate by plugging it in, or you could look at the graph, the limit from the left, the limit from the right. They're both approaching that same point, and that point is at a y value of 2. So that's really nice, right? The bottom function and the top function around 0, those both have the same value. So what do we think must also be true about this middle unknown function? Well, if the bottom and the top function, if they meet, if they squeeze together, well then that function in the middle, f, oh, someone's honking, they're mad, then that function in the middle must also go through that same point. Now it may be an empty dot, like we don't know the function is defined, there could be an empty dot there, but that empty dot doesn't affect the limit. I know as I approach from the left, and as I approach from the right, that function f, even though it may potentially be undefined, it's supposed to be right here at 2 in the middle. If the upper and the bottom, if those bounding functions meet, if they compress together and squeeze that middle function, then that middle function must also have the same value. And then we would want to say, by squeeze theorem, right? Anytime you say something, remember that means therefore. Anytime you're going to use a theorem, you should always cite it. So we know that middle function f, as x goes to 0, is going to have a limit value of 2. How do we know that? Well, because we checked, we did the math, and we're also citing by squeeze theorem. Okay, one more, and then we'll be done. Short video for this. I'm probably going to add it on to either the previous day, or I'm going to add it on to the next day with the continuity. Oh well, it's pretty quick. Here we go. Graph the given function and the equation absolute value of x and negative absolute value of x in the same viewing window on your calculator, and then squeeze theorem to find the limit of the function f. Now, I don't think you guys should know what that graph looks like, right? It's a very weird little graph. I would not expect you to know what it looks like, nor going forward am I going to need you to know what it looks like. This question, it really tells us to use a calculator, so that's nice. The calculator could get that pretty well. You should know what that function looks like, right? The absolute value function. It's like this. And then the negative version of it looks like this. So you should be able to graph those bounding functions, but that one in the middle, which is kind of weird, you shouldn't really know, and don't stress about knowing what it is, right? I'm going to kind of sketch the graph that I have here from my notes. I'm not going to bother getting out my calculator. It dips below the x-axis, but then it comes back over, and then it does kind of the same thing on the other side. It's symmetrical, I think. So that function, you can look on your calculator or on Desmos if you want. It looks more or less like that if you zoom in close enough. But if you look at it, it appears that that absolute value function on the top and then that negative version on the bottom, it looks like that's going to end up bounding that function. And if that function f is bounded in between the two, well then we could use squeeze theorem to get this limit done. But before we can use squeeze theorem, I really have to make sure that this inequality is true. Because if this isn't true, then you can't use squeeze theorem. You need this inequality to be true, and you need the bottom piece and the top piece to end up having the same limit value, which it really looks like they are, right? Both of those absolute value and the negative version, they're going to go through the origin. But we really have to confirm that that function is going to be bounded between the two. So let us think about something, right? This is kind of a little bit weird and a little bit conceptual, but try to follow, right? This function, we're going to break it down. Focus on this part first. If you have sine of something, sine of stuff, right? The 1 over x inside doesn't matter. The sine function is a naturally bounded function. I know this is always, ooh, I can't spell, that was really bad, always going to be bounded between two numbers. It's between -1 and 1. It doesn't matter what's inside the sine, right? That sinusoidal wave is always going to be bounded between -1 and 1, right? That sine function. Sine of stuff is always going to be bounded between -1 and 1. So now let's think, like worst case scenario. Let's write this inequality. Worst case scenario, like let's assume it's like as big as possible. So let's assume 1. So if this part is 1, the biggest that the f function could be overall, like if you have multiplication, I've got these two chunks. I've got the x chunk, and then I've got the sine chunk. If I were to think about this kind of worst case scenario, like the biggest possible thing this sine function could be is 1, that means the biggest possible thing this f function could be is x times 1. And then on the other end, the smallest this could potentially be is -1. So then if you're looking at the f function as a whole, the smallest that f function could ever be is -x. Right? Another way to think about it, if you take this inequality, multiply by x. So now I have this. Now this function ends up looking like this, right? That's your y equals -x. Oops, it's off the screen. That's my bad. I'm sorry. I should check the screen more often. And then this one over here, we should know that y equals x. If there's only one linear function you can graph, I hope it's that one. But we know what the -x and the x functions look like. And we know this function in the middle, it's always bounded in between. And you're saying, well, Mr. Bell, that's great, but here it's telling us about the absolute value and the negative absolute value. Well, that's because for squeeze theorem, you really wouldn't want your two graphs to cross over, right? So if I were to do both of these on the same coordinate grid, you would have the -x function, and then you'd have the y equals x, the positive function. But if you look, right, that's the y equals x, that's the y equals -x, and then it says, hey, that function's going to always kind of be restricted between those two. Worst case scenario, it's always going to be bounded in between them. But for the squeeze theorem purposes, instead of taking this function and this function as the bounds, we want one of them to always have the top, and then we want the other function to always have just the bottom part of these two graphs. So instead of using the two graphs for negative x and x, they're going to use the absolute value functions. They're going to generate the exact same graphs. Like graphing these two things and then graphing these two things would give you the exact same looking graph. But for squeeze theorem, we need one function to always be on the top, and we need the other function to always be on the bottom. So instead of using x and negative x, which cross and switch positions, we'll use the absolute value and the negative absolute value, which don't. Right? So a little bit weird, not terribly important if you follow it at all. What you'd really just have to do at the end of the day is take the limit of the top function, which we can see is going to be 0 as you approach from the left, and as you approach from the right, you're approaching the origin. And also the limit as you approach 0 for the negative absolute value function. It's also going to be 0. That's really lovely. Those match, which we like. So therefore, I know, you don't necessarily have to prove this, right? I mean, I hope you would be able to, but you don't really have to. Therefore, I know the limit as x approaches 0 of this weirder f function, right? We kind of already proved that it's going to be restricted, but you could kind of just look at the graph and also see it. I know that limit is also going to be 0 by squeeze theorem. Or sandwich theorem. That's the same thing. Squeeze, sandwich, I don't care. You either squeeze that middle function down to that same limit value, or you can sandwich it. Whichever word sticks in your memory the best, that's fine. But there's your squeeze theorem. It's the first of many little tiny small theorems that we're going to be doing throughout this year. They're going to come up, and then I'm going to teach them to you, and then we'll have like 1 or 2 or maybe 3 homework questions over it. But there's not going to be a whole lot this year over squeeze theorem. So just kind of be warned, right? I would put a little star in your notes. This squeeze theorem is something that come like late April time or early May before the AP exam. You probably want to come back and just do a little bit of a refresher over squeeze theorem, because it's going to be really easy for you to forget it. But if you just do a little bit of studying at the end, like it takes like 2 or 3 minutes to remember what this is, if you remember it, then there may be a free question on that AP exam. Like if there's a multiple choice over squeeze theorem, that's for sure going to be like one of the 2 or 3 easiest questions on the whole test, right? So even though we are not going to do a whole lot with it in my class, it's something you would want to kind of bookmark, dog ear, save it for later. Make sure you come back and you review it at some point, so that way you don't miss a potentially easy question on the AP exam.